there are three equations you need to be able to apply from D1. This one is to calculate brightness. So the brightness of, let's use the sun as an example. So brightness means intensity. It means the power per unit area arriving from something. So you can calculate the brightness coming to the Earth from the moon, for example, or the sun, or any star. Obviously, the sun will be the main thing. So that's equal to its luminosity over 4 pi d squared. Let's think about that for a second. Here's the sun. Luminosity is power. Lots of confusing things to measure about stars. There's brightness and luminosity. There was also magnitude. Nice and simple, luminosity is power. So if you imagine luminosity, so power, being spread out from here, that's number of joules per second, and the luminosity of the sun is about 3.8 times 10 to the 26 watts. That's being spread out, and every second it will form a big sphere around here. And of course the area of that sphere, I'm sure you know, is 4 pi r squared. So if we're distance d away from it, then that power we spread out over a sphere with surface area 4 pi d squared. Notice also I've used this circle with a dot in the middle. That's our symbol for the sun. Same as in astrology, that's our symbol for the sun. You might know some others, Mars and Venus, for example. There's Mars. They all have their own symbols, but the sun is the one you're going to get used to, I hope. So let's work it out for the sun, get from luminosity to brightness. So brightness of the sun is the luminosity of the sun over 4 pi d squared. That's the distance to the Earth, but you can use any distance, of course. So that's 3.8 times 10 to the 26 all over 4 pi d squared. So that's about 152 million kilometers. So we'll call it 1.52 times 10 to the 11 meters squared. So we're going to use SI units. We could have done it in per square AU, but that's a weird unit. So if you work that out, it comes out to that. So roughly 1.3 kilowatts per square meter. And that's called the solar constant. That's a known result. The solar constant might be more like 1.4, but with a bit of rounding error, that's about right. That means if you had a square meter solar panel and held it up flat onto the sun, 1 AU away from it, so just above the Earth's atmosphere, that's the maximum you could ever get with perfect efficiency. About 1300 watts is what you get. So we obviously get less than that because the atmosphere blocks a bit out, etc. But that's our solar constant there. So you can think if we were twice as far away from the sun, we'd only have 1/4 of the brightness. So it's a measure of the intensity due to something, calculating brightness there.